Well, hello everyone, and welcome to Prep 3.2. So in this prep, we're going to look at the central limit theorem and its importance to pretty much the rest of the class. But before we begin, we're going to do a little exercise. So as you can see here on this tab, we have lots of population data along the left. So this is data about profits at different automobile and dealerships, profit per sale. Then if we wanted to sort of see, well, what does that look like? What does that data look like? We can get descriptive statistics about it and then graph it. So we're going to begin with that. So we'll start out by getting the mean. And then we'll get the standard deviation. And it's dot P because it's population. Okay, now with those two numbers, we can actually calculate the data points for the normal distribution corresponding to that data. So we're going to do that here in this population column. And you can see here that we have profits evenly spaced. So these are going to form the x-axis. And then we're going to calculate, well, what would the y value be? What would the probability be at each of these values? And we can do that, believe it or not, just with those two numbers using the norm.dist function. So we do norm.dist. There's the first number, the 200, and here's our mean, which we lock, standard deviation, which we lock, and then usually we put true here, but this time we're going to put false because we don't want cumulative, we want that point so that we get all the little points on the curve and get the whole curve. And then if we copy this down, it will automatically build our graph, and there you can see it. So that's what our data looks like. And the mean is right here at 1843. All right, now we're going to make 3 more curves on the same graph. But each of those curves is going to represent something different. And the next curve that we're going to do is going to represent, well, what happens if instead of plotting individual data points, we plot samples that we take from that data. So these are 15 different samples of 2 taken from the data. They're random samples, and they're taken from the data on the left. And so we're going to begin by calculating the average value of each sample, dragging that across. And then we'll get the standard deviation also. And this is .s because they are samples. Okay. Now, to plot this data, what we're going to do is calculate, this is where n equals 2, sample size equals 2. We're going to get the average of all those samples. So think about it, we're getting the average of the averages. So it's going to be the average of all these guys. And then we're going to get the standard deviation. And that's .s because they're samples. The standard deviation of those sample means. So come right back to that means line and get the standard deviation. All right, now, this gives us the shape of the line for n equals 2. So we come back to the norm.dist to plot it. So the x-axis stays the same as it was in the last case. There's the mean, lock that, standard deviation, lock that, and put false again. And then copy that down. All right. Now, the structure of the line has changed. It's hard to see here unless you get right to the end, but this line is made up of basically a series of little triangles. And I'm using the triangle symbol to represent a sample. So effectively, this is the distribution, not of individual data points, but it's the distribution of sample means. Which sample means is it a distribution of? It's a distribution of sample means of size 2. All right, what if the sample mean is a lot bigger? What if we go to a sample mean of 30? And that's what happens next down here. So let's go ahead and do that. Equals average copy that across. Oops, shouldn't have copied that down. There. And then we get the standard deviation. For each of them. And if you're wondering, well, why haven't I referenced these standard deviations yet? It's because I will, but for what we're doing so far, they're not needed. All right, then come back up here, and we're going to do the equals the average of these sample means. So the means of the means. And then we want the standard deviation of those same sample means. Okay, now we'll plot that. So we'll call this equals norm dot dist x mean standard deviation false. All right, so this is really interesting. Again, we're using the marker of the triangle to indicate that this is a plot of sample means, not a plot of data points. And think of the triangles like little mini distributions, but that was the only symbol that they had that was even close to a bell curve. Okay, and what I want you to see right away is that this curve, n equals 30, is skinnier than the n equals 2, which is skinnier again than the population. So what's going on here? In other words, why are the sample means all clustering around the population mean? And that's where the central limit theorem comes into play. So before we finish this off, we're going to look at this theory over here, and this is really important because some of our questions are based on it. So in this assignment, we transition from the probability of a single value to the probability of a sample mean. Let's begin by considering things that intuitively make sense. So a sample mean will approach the population mean the larger the sample, right? Because if the sample gets big enough, eventually it's going to be the whole population, so the means will be the same. The mean of an infinite number of sample means will be the population mean. Some will be high, some will be low, but they will average to the true population mean. And that's kind of cool. And you can sort of see this starting to happen here. Remember, this is the true population mean. Here we had a bunch of samples. Okay, so this one ends up being averaging a little low. The n equals 30, those are averaging a little high. But if we had kept doing this like a million times, eventually this one would have been spot on, and so would the n equals 30. A sample mean is more likely to be closer to the population mean than a randomly chosen value from the population. So for example, if I pick a student in class and ask their grade, there is a chance that it'll be a failing grade, far from the mean. like if a student's just not doing their work. But if I average the grades of 2 random students, there's less chance that the average will be a failing grade. I mean, like, what are the chances I'm going to pick the only 2 students in class that had a failing grade? And if I up that to 10 random students, there is no chance that the average will be a failing grade, because the chances are just ridiculous. In fact, I don't think we've got 10 students in class. In fact, I know we don't, that have a failing grade. So a sample of grade averages tends to approximate the class average. In other words, you lessen the effect of the extremes. Number 4, a deviation from the true mean is more probable for an individual value than for a sample average, which is another way of saying 3, even if the numerical difference is identical. So what that means is, for example, if you had a value out here on the population, it wouldn't be that much of a crazy outlier, but it's a total crazy outlier for n equals 30. I mean, the probability is almost 0. Okay, a variance of a sample will be closer to the variance in the population, and it gets closer as the sample size increases. In a pinch, you could use the variance of a sample as a stand-in for the variance in the population, and this actually happens in a t-test. So what this is the reason that we did this sample standard deviation line here, was to make this point. So you can see in sample size, remember, we know that the actual population variance or standard deviation is 1843. And if we look at these, that's my bad, that was the mean. The standard deviation is 641. That's the population, is 641. Now, if we look at these, these are all over the map as far as not being particularly close to 641. I mean, some are high, some are low, some are ridiculously high, some are ridiculously low. But when the sample size increases, notice how they sort of level off and get closer to that 641. I mean, there still are, a few extremes, but there's not as many extremes, because as the sample size increases, the variance approaches the population variance. So in a pinch, you could use the variance as a stand-in for the variance in the population, and this actually happens in a t-test and will happen in this exercise. However, you cannot use the mean of the sample as a stand-in for the mean of the population, since almost every statistical test involves comparing the 2 means. All right, now we get to the central limit theorem. This is what it's all about. The central limit theorem states that as the sample size increases, the distribution of sample means will approximate a normal distribution, regardless of the shape of the population's original distribution. So even if the underlying population wasn't normal, the sampling distribution of the sample means would be. And that is called SDSM, sampling distribution of the sample mean, and the grand mean of SDSM is called capital X bar. All right, mean and variance. The mean of the sampling distribution, or capital X bar, equals the population mean. So what this is stating is that this mean, right, because this is a sampling distribution, so is the green one. So the mean of both of these sampling distributions is the same as the mean of the population, which is the population mean, 1843. And the expected variability, and the reason for that is because some are going to be high, some are going to be low, but it's going to average. The expected variability, or standard error, of the sampling distribution is given by sigma divided by the square root of n. This turns out to be a really big deal, because normally the variance is just sigma. When you divide it by the square root of n, interesting stuff happens, right? Because you divide any number by another number, that number gets smaller. So the variance of a sampling distribution is going to be smaller than the variance of population. You can see that right here. Population's all spread out. The sampling distribution starts getting tighter. And the bigger the n, right? There's the n. The bigger the n, in this case 30, the tighter it gets. So the bigger the n, the smaller the standard error. For example, 20 divided by the square root of 100 produces a standard error of 2, whereas 20 divided by the square root of 25 produces a standard error of 4. The bigger the n, the skinnier the sampling distribution, because less variability among sample means results in a skinnier curve. The rate at which SDSM gets skinny slows down. The square root of 25 is 5, but the square root of 100 is only 10, and not 4 times 5, which would be 20. This is good news for researchers, since it means that getting larger and larger samples has diminishing returns, A random sample of 30 in many cases is good enough, and you'll see that in our exercises. The sampling distribution curve will be skinnier than the population curve. We already saw that, right? Skinnier than the population curve. If you divide sigma by another number, it gets smaller, so sigma divided by the square root of n is less than sigma. In other words, the variability of the sampling distribution, what's called standard error, will be less than the variability in the population. And finally, for the SDSM, z-scores are computed as the difference between the sample mean and the population mean, so you subtract those two, and divide that by the standard error. So if the standard error is small, then even minor differences between the means are going to lead to high z-scores, because if you're dividing by a small number, then you haven't really reduced your number by much. You haven't reduced the numerator by much, so your z-score goes up. And if your z-score goes up, your probability goes down. And we will see all of that in these exercises. So now, with all these things in mind, we can do something unbelievably cool, because we don't actually have to do this exercise. We sort of did this as a way that you could see where all these numbers are coming from. But the fact of the matter is that theoretically, from the central limit theorem, we can actually compute what the sampling distribution will look like without having any samples at all. In fact, all we need to do, right, is know the sample size and sigma. So here we go. So the grand mean is going to be equal to the population mean, because that's given by central limit theorem. They're going to have the same mean. And the standard error is given by sigma. So there it is. You already had it. Sigma divided by the square root of n. And we're going to say in this case that n equals 30, because we're going to try to match theoretically the line that we've already drawn. Remember, this line was drawn with real samples. This is going to be a theory line, this next one. So now let's plot that theory line. Norm dot dist x mean standard deviation, or standard error in this case, and false. Copy that down. So this blue line, and you're going to see this blue line on the following pages, this blue line is our theoretical sampling distribution of sample means. And you can see that the theoretical almost matches perfectly what we did empirically. And that's really cool, because it means we don't really have to do the empirical. The theoretical is going to do the job. And that becomes incredibly useful. So thank you very much, and we'll see you in the next video.